For those of you who do not know who Professor Harry Seed is, I was actually checking very quickly. There's a very nice biography on Wikipedia that you can take a look at. But let's help our younger members. Professor Harry Seed is a pioneer in the field of earthquake engineering. He laid out the framework of many of the techniques, tools, procedures, approaches that we take almost for granted nowadays in the evaluation of projects, seismic effects, their impact on our earthquake impacts on infrastructure in a systematic yet practical way. And that's really was the genius of Professor Harry Seed. Professor Kramer will say a little bit more about Professor Harry Seed, and of course Professor Kramer studied with Professor Harry Seed. And it's really a fitting honor to have Professor Kramer be the Seed lecturer. So a little bit about Professor Kramer. He joined the Geotechnical group at the University of Washington in 1984, and he has been a faculty member there since. He has an interest in a number of areas and contributed to it: site response, liquefaction, seismic slope stability, and hazard analysis. His work has been recognized in many, many ways, from the early days as a recipient of the Presidential Young Investigator Award of the National Science Foundation, Arthur Casagrande Award for IFCEE, Walter Huber Award, and he was named the 2012 Academic Engineer of the Year by the Puget Sound Engineering Council. For most of us, we know Professor Kramer through his book, Geotechnical Earthquake Engineering. And this is a book that has really advanced seismic safety across the world. It laid out the framework of how you would approach geotechnical issues due to earthquake shaking in a way that allowed people, engineers stateside and worldwide, to tackle these problems in a way that allowed them to approach them again in a simple yet fundamental way. And so the profession and communities around the world are going to be indebted to Professor Kramer for many years for improving and raising the level of seismic safety. So now we're going to go through the real reasons of why Professor Kramer is receiving this award. First, the good looks and the hairdo. Okay. And as you can see, and I'm trying to follow his, hairdo things. The other thing about Professor Kramer and why he's receiving this award, because he was the real force that allowed Berkeley, the Berkeley Geotechnical Group, to consistently beat the Stanford Geotechs at volleyball and basketball. He was the MVP. But also, however, the reason you do not know of him in that capacity, because people knew him as Brian Sweeney. So that's how he introduced himself. A little anecdote also about Professor Kramer. He is known as a hacker and a jokester. Probably wondering what it is. Apparently, in the early days of computers, he would manage to go in and send emails at the University of Washington from certain people to some people with a certain colorful context. And so, also, those of you who know Professor Kramer, he has a wonderful and unique sense of humor as well. I was also told that Professor Kramer met his wife, Diane, who joined us today at the Dutch Goose. And so please join me in recognizing Diane Kramer, who is with us. Diane, please. So I've also had the privilege of knowing Professor Kramer personally, and I've worked with him on project, and as well as had the fortune to visit their house. It is really it's an amazing experience to work with Steve. It's just, he has a very even keel approach to dealing with problems when things are going up and down. It just, call him up, we talk about things, and, I just sort of get to see the big picture. So it's been really a privilege, Steve, to work with you. Now, in terms of even more personal, the thing that has been really memorable for, my family visited their house, was playing golf in their hallway on the top level. That was so much fun. In fact, when I told them I was here to introduce Professor Kramer, says, didn't we play golf there? So if you get the privilege of visiting the Kramers, remember to play golf. So without further ado, I would like to invite Professor Kramer to come up here and receive his medal. Okay. Put it here, or give it to them. And Professor Kramer will share with us his lecture. Thanks.
Well, thank you, Yusuf, for most of that kind introduction. It's a great pleasure and a great honor for me to be here and to deliver this lecture today. I'd like to thank the Geo-Institute for recognizing me with this great honor. Thank those who nominated me and supported my nomination. I'll be speaking today about performance-based design for soil liquefaction. It's a further pleasure for me to be doing it this week with the other GI members who have been honored as a Peck Lecturer, Rich Finno and Rudy Bonaparte, the Terzaghi Lecturer. Rich and I shared an office in the summer of 1977, and Rudy and I shared an apartment in Berkeley as graduate students in 1978. So I think all three of us are probably amazed to be recognized in this way some 40 years later, and particularly to get to do this during the same week. It's been a lot of fun. I'd like to also acknowledge some of the organizations that have supported my research, and particularly in this area of performance-based design and evaluation. Pacific Earthquake and Engineering Research Center, the Pierce Center, and the Washington State Department of Transportation. I'd also like to acknowledge my colleagues, my good friend and colleague Pedro Arduino at the University of Washington, and graduate students Roy Mayfield, Young Suk Shin, Kevin Franke, Yimin Huang, Sam Sedaris, Mike Greenfield, and Andrew McDeasy. I'll start by saying a few words about Professor Seed, and then talk about design and performance, uncertainty in its role in performance and performance-based design, some different ways that we can implement performance-based design, and I'll conclude with some comments on the implications and opportunities of performance-based earthquake engineering for professional practice. Harry Seed, as Yusuf said, is the undisputed father of geotechnical earthquake engineering. He began working on these problems shortly after the 1964 Niagara and Alaska earthquakes, where he dove in and looked at a number of problems and continued working on those throughout his career. Following his untimely death in 1989, ASCE instituted the Seed Medal. It's a unique medal in that it's given every other year to someone working in the geotechnical earthquake engineering area, and in the other years to general geotechnical engineers. And when I look at the list of seismic Seed medalists, I see names of people that I have admired and looked up to for many, many years, going back to my graduate school days. And it's really an honor to think that my name is going to be part of this list from now on. I first encountered Harry Seed when I was 20 years old in winter quarter 1976 at Berkeley, and I took my first soil mechanics class. I went down to the basement, we don't play golf down there, and found my old notebook from that quarter. And I was looking through it, and on February 9th, 1976, I saw the word liquefaction for the first time. I went to grad school at Berkeley. I took a couple more classes from Professor Seed there. The Geotechnical Earthquake Engineering class reader consisted of 13 of his papers. They were about 3 inches thick, and they were fantastic papers, classic papers. But I remember at the time thinking, somebody ought to write a book on this stuff. I returned after 3 years in consulting to do a PhD. I was lucky enough to be asked to do a work on static liquefaction by Professor Seed, who had been put in charge of the forensic investigation of a large landslide that occurred at the port of Nice as they were expanding their airport there. And Professor Seed was heavily involved with this. I did laboratory testing in support of the investigation. He then moved on to be in charge of the Aswan Dam investigation. He was traveling a lot during those days, and I really treasured the time I was able to spend with him, where I learned a great deal. My daughter the other night asked if I had any pictures of myself with Professor Seed, and I said, no, I don't. We didn't carry cameras around with us all the time then, and it cost money, which I didn't have. But then she reminded me that I had a picture from my graduation, so I decided I would show it. It's Berkeley engineering graduations are held at the Greek Theater outdoors, and I'm there receiving my diploma from Jim Mitchell, who's looking at me as I'm looking at him. I'm pretty happy both to have my diploma in my hand and to have a full head of hair on top of my head. Everybody else is happy. The tradition there was for the advisor to put the hood over the head of the PhD student. And Professor Seed, although he was a giant in geotechnical earthquake engineering, wasn't a very tall man, and it took him 3 tries to get it over my head. And so he finally did, and you can see some of the reaction. If you're an earthquake engineer, you may recognize some of the names of very prominent and famous people that were there at that time. Professor Seed won more ASCE awards than any other civil engineer has. He is a member of the National Academy of Engineering and the National Academy of Science. He's a recipient from from President Ronald Reagan in 1987 of the National Medal of Science. That book did get written, as Yusuf said. It turned out that I was the one to write it, and as I went through and prepared that book, I realized even more than I had previously, both the depth and the breadth of his contributions to geotechnical earthquake engineering. They really were remarkable. When I go back and look through the reference list, there are about 900 references, and almost 10% of them are reports written by Professor Seed. When I went through and counted up the 2nd, 3rd, 4th, and 5th highest number of references by people with names like Idris, Ishihara, Dobry, and Yaud, they added up to 2 less than Professor Seed's. So he really was a remarkable man, and it's a great honor to be asked to give this lecture. So let's talk about design. In geotechnical design, we start out typically by defining some performance objectives that we'd like to achieve. We characterize the loading that we anticipate, select a design approach, and develop a preliminary design. We then analyze that preliminary design to determine whether or not it will have met our performance objectives. If it doesn't, we modify the design and we go back and analyze our modified design and keep looping through this process as many times as we need to until we've met our performance objectives, and then we can move on to construction. We often define our performance objectives in a pretty informal way, and it does us well often to think more explicitly about what we mean by performance. We can look at it in terms of demands exceeding capacities, and we usually do that, or at least historically have done it in geotechnical engineering, by expressing both in terms of forces or stresses. We compare the two by means of a factor of safety. We recognize that demands are uncertain, that capacities are uncertain, and we account for those uncertainties and the consequences of a failure in selecting a minimum allowable factor of safety for design purposes. We can also look at performance in terms of deformations. There may be vertical settlements, there may be lateral deformations or some type of rocking deformations. But our deformation demands are uncertain, our deformation capacities are uncertain. We account for those uncertainties and the consequences of failure in selecting some maximum allowable level of deformation that we can design for. We can look at performance in terms of physical damage, maybe the cracking of a floor slab, spalling of concrete from a column, or hinging of a pile. Maybe catastrophic damage that could lead to collapse. Damage states such as these are all uncertain. We can also look at losses as a performance objective. High repair costs, loss of serviceability of a system or a structure, or casualties. Performance, we should recognize, means different things to different people. If you talk to a seismologist, they may say spectral acceleration or peak acceleration is a good indication of performance. To a geotechnical engineer, we might look at the displacement of a slope An estimator may look at the width and spacing of cracks that need to be repaired in some slab. An owner is concerned with money, with finances, and they look at things from a financial standpoint. The process that leads us to performance begins with ground motions. The ground motions excite some system that we're interested in. It might be a building, a bridge, a dam, a pipeline. If that response is excessive, we'll see some form of physical damage, and that damage leads to losses. Losses might be the cost of repairing bridge columns, say with steel jackets as shown here, or it may be something that's much more difficult to try to quantify. Performance-based design concepts started coming out in the 1990s or so, and they were first formalized by the Vision 2000 report that came out in 1996. It advocated design for multiple return periods, 4 different return periods, frequent, occasional, rare, and very rare ground motions, with 4 different levels of performance objectives: fully operational, operational, life-safe, and near collapse. Some of those combinations were considered to be unacceptable. We don't want to have design structures so that they're on the verge of collapse in frequent earthquakes. For typical earthquakes, typical structures, they were intended to be designed to be fully operational following frequent ground motions, operational following occasional motions, life-safe in rare motions, and to not collapse in very rare motions. Essential or hazardous facilities or structures, such as hospitals, police and fire stations, emergency communication centers, were held to a higher standard. Safety critical structures, such as structures that might contain toxic or radioactive or explosive materials, to a higher standard yet. Ultimately, what we're interested in the end are these losses. These are what we want to try to minimize. They come from physical damage. The physical damage comes from the response of a system that we're interested in, and that response is excited by ground motions. Usually in engineering, we start at the beginning with a ground motion, and we use a response model to predict the response of the system we're interested in. It may be something as simple as an empirical model that we can put into a spreadsheet or solve on a calculator, or it might be a multidimensional, nonlinear, effective stress finite element analysis. We could take our system response and predict damage by means of a damage model, and we use that damage to predict losses by means of a loss model. There are a lot of terms that we can use to describe each of these quantities, and so we need some terminology to make this communication a little bit easier, and I'm going to use the terminology that Peer had developed. So we use intensity measures to describe earthquake ground motions, engineering demand parameters to describe the system response, damage measures to describe physical damage, and we'll call losses decision variables. So our response models allow us to calculate the response or predict the response of the EDP given some level of ground shaking or intensity measure. And our damage models predict the damage measure given the EDP. Our loss models predict the value of the decision variable given the damage. All of these things are uncertain. The quantities themselves, the variables are uncertain, and these models introduce uncertainty. And we have to recognize that uncertainty is there. It's real. We can't ignore it. There's uncertainty in ground motions that vary from location to location. Our uncertainty is different in the western U.S. than it is in the central and eastern U.S. There's uncertainty in response from site to site. We have different soil conditions. Things respond differently. Different types of structures respond differently to the same ground motion. There's uncertainty in damage from structure to structure. Steel buildings and concrete buildings get damaged differently. Tall and short buildings are damaged differently. There's uncertainty in loss. It varies with location. Material costs and labor costs are different in different locations, and costs change over time with inflation, interest rates, and other things that are difficult to predict. We have to recognize that one size doesn't fit all when it comes to handling uncertainty. We need to look at individual situations. If we ignore uncertainty or assume it's the same everywhere, we're going to end up with inaccurate predictions of performance, with inconsistent levels of safety from one location and one project to another, and inefficient use of resources that we have to retrofit or design new structures. So it's different approaches that we can take. A discrete approach, we can divide up the possible ranges of response, of ground motion response, damage, and loss into a number of categories or ranges. If an earthquake occurs, we might assume that there are only 5 levels of earthquake shaking that can occur, denoted by intensity measures 1 through 5. Maybe we're at IM2. And if that's the case, maybe we can have 5 levels of response that are generated. Maybe EDP level 4 occurs. There could be five levels of damage. Maybe we see damage measure number 3. And we can have 5 different levels of loss. And we have decision variable number 5. So we've got a path defined through this network from IM2 to EDP4 to DM3 to DV5. If we want to predict the loss associated with that DV5, it's going to be equal to DV5, but we have to multiply it by the probability that the intensity measure really is IM2, given that an earthquake has occurred. The probability at EDP, we're at EDP level 4, given that our intensity measure was IM2, and the probability of being in DM3, given that EDP was EDP4, and the probability of DV5, given DM3. That's one path. We sum these over all paths, and we get the expected value, or the average value of the loss that we can expect. For this case, we'd have to go through 625 paths. If we discretize things in a more refined manner, the number of paths increases very, very, very quickly. So we can look at another approach, what we might think of as more of a continuum or integral hazard level approach, and look at all ranges of ground motion, account for the uncertainty in these parameters and their relationships. And such a model was developed, a framework by PEER, the Pacific Earthquake Engineering Research Center, in the form of the well-known, famous, infamous triple integral, which is not as complicated as it looks. First part is the result of a probabilistic seismic hazard analysis. We do these things all the time. They tell us how often we expect to see different levels of ground shaking. Usually we do these by going to the USGS website and getting that information, but for special projects or important projects, we do site-specific response or probabilistic seismic hazard analyses. The next part comes from our response model. We use a probabilistic response model and express the results in terms of fragility curves that tell us the probability of exceeding a certain level of response given some level of shaking. So we have a family of these fragility curves. And similarly, we'll have a family of fragility curves that express the results of our damage models and our loss models. We integrate over the ground motion, response, and damage, and we end up with a loss curve that tells us how often we can expect to see different levels of loss. The vertical axis here represents a mean annual rate of exceedance, which is approximately an annual probability. So we'd have a 1% probability in this case of having a loss of $2.7 million or more. Every 1,000, we'd have a 0.1% probability of a loss of $5.8 million. The reciprocal of that probability is the return period. And so our $2.7 million loss would have a return period of 100 years. Every 1,000 years, we'd expect to see a loss at or exceeding $5.8 million for this particular design. If we try an alternative design and go through the same process, we'll get a different loss curve. And for this one, our 100-year loss now is down to 1.6 million, and our 1,000-year loss is down to $3.9 million. Better performance, at least expressed in terms of losses. Well, that won't come free. There's going to be some extra cost involved in providing that extra margin of safety or that reduction of loss. But within this type of a framework, a performance-based framework, we can compare the benefits that we get in terms of reduction of expected losses with the cost of providing those. And we can do it in the kind of terms that the people who hold the purse strings on making decisions about how to handle seismic resilience are going to appreciate and respond to. One of the benefits of the PEER model is that it's modular. We can take a ground motion hazard curve, combine it with a response model, and get a response curve. We can combine that response curve with a damage model to get a damage curve, and we can combine that damage curve with a loss model to get our loss curve. And if we go through that whole process, we've included the effects of all earthquake magnitudes, all source to site distances. We've accounted for uncertainty in the ground motion, uncertainty in the response given the ground motion, uncertainty in the damage given the response, and uncertainty in the loss given the damage. So we've explicitly calculated all of these quantities with proper consideration of the uncertainty that's involved in each of them. Now, usually those relationships are complicated enough that we can't carry out those integrations in an analytical form. We have to do them numerically. But if we make some simplifying assumptions, we can develop a closed form solution, say, for a response hazard curve. So if we assume that a power law describes our ground motion hazard curve and a different power law describes the response model with log normal uncertainty, we can combine these things to get a closed form solution for our response. If we look at it more closely, we'll see that there's two components to it. One that's based on the median ground motion and the median response model. relationship, and the other we can interpret as a response amplifier, because it has a value that's equal to 1 if the uncertainty is 0, and a value that increases as that uncertainty increases. So we can take this approach and extend it to the damage measure and the decision variable, making the same basic assumptions, and we'll see again that we have two components, one that's based on the median relationships, and another that's based on uncertainties and serves as an uncertainty amplifier. But now it includes uncertainty in our response model, uncertainty in the damage model, and uncertainty in the loss model. And if we look at the results of this analysis, first neglecting uncertainty, just looking at the median relationships, we might get a curve that looks like this. If we add in the response model uncertainty, it's going to move up and to the right. If we add in the damage model uncertainty, it moves some more, and the loss model uncertainty causes it to move even more. So for a given return period, a given annual probability of occurrence, our losses go up as the uncertainty increases. And so one of the things we do as engineers is to reduce uncertainty. We do more detailed subsurface investigations, we do better and more laboratory and field testing, we do more detailed analyses, and we can reduce uncertainty, and that reduces the losses, the expected values of the losses, and that improves the value of the structure or system that we're dealing with. So how do we implement these performance-based concepts? There are a number of different ways we can do that. After we characterize the loading, we have to decide how we're going to characterize performance. Are we going to do it in terms of response, in terms of physical damage, or in terms of losses? We can do all three of these things. If we do it in terms of response, we're going to use a response model to explicitly compute the response due to some level of ground shaking. We're then going to infer, without calculation, the damage, so it's going to be a little fuzzy, and we're going to infer the losses from our inferred damage, so it's going to be fuzzier yet, more approximate. This requires that we characterize and obtain, define allowable levels of response. Could be expressed in terms of forces, stresses, moments, or a factor of safety, or in terms of displacements. And we know that physical damage is more closely related to displacements than it is to forces. And this is the way that performance-based design is currently done. It's implemented at this level where we're looking at deformations. We could, in many cases, substitute displacement-based design for most of the analyses that we do and call performance-based design. Whichever way we do it, we'll end up comparing some predicted level of response with an allowable level of response for one or more ground motion hazard levels. If we apply this to liquefaction, we characterize our liquefaction potential, the potential for initiation of or triggering of liquefaction, by means of a factor of safety that's a ratio of capacity to demand or resistance to loading. Our resistance typically comes from an empirical correlation to penetration resistance, or in some cases shear wave velocity. Our loading comes from the simplified method. It's a function of the peak acceleration and the magnitude of the earthquake that produced that peak acceleration. So our peak acceleration comes from a seismic hazard curve. We choose a return period, come across, and pick off the corresponding peak ground acceleration. But we should recognize that there could be multiple seismic hazard curves that pass through that same point. If they had the same underlying magnitude, then we'd have the same liquefaction potential for all of these cases by the conventional procedures that we use. But if we use a longer return period, we'll find out that liquefaction potentials are not the same. So the actual liquefaction potential depends on the whole seismic hazard curve on all levels of shaking. So the way we do things now is to typically choose a return period, find the peak acceleration, calculate the corresponding magnitude from a deaggregation analysis, compute our cyclic stress ratio, get the cyclic resistance ratio from our penetration resistance, and we calculate a factor of safety. And we conventionally want to see that factor of safety have some minimum value that might be in this range. So what we've done is to take a probabilistic representation of our ground motion hazard and combine it with a deterministic representation of the liquefaction potential at one level of shaking. So we have one peak acceleration, one magnitude, and one cyclic stress ratio. So let's talk about football. We're here in Florida. It's a good sport. A lot of good football players come out of Florida, but we're not all from Florida. We're not all from the United States. So a little review. 11 players on each side. They come in different sizes, they run at different speeds, and there's different consequences when they hit you. They're free safety on defense, relatively small guy, very fast. They run all over the field. They're hitting people all the time on every play. They are a big factor. Middle linebacker is bigger, not quite as fast, but those guys are still fast. They make most of their tackles in the middle of the field. And we've got the defensive tackles, the big pigs, 300 pounds or more. They don't run as fast, but when they hit people, they hit people. So there's a lot of different hazards out there for the offense. If you're an offensive coordinator, that you're designing plays and calling plays, you have all these threats. You have these fast guys running around hitting you all the time. You have the big, slow guys that are gonna crush you if they hit you. If offensive coordinators called plays like we do liquefaction analyses, we would see that they only block one player, the middle linebacker, say. The smaller players that hit more frequently and are a distinct threat to the success of our play, we ignore it. The bigger players hit more rarely, but with more force, we ignore, just like we ignore earthquakes or ground motions of the size other than the one with our associated return period. So we can improve this procedure, and we have done this with a modified version of the peer framework. My student Roy Mayfield did this as part of his PhD work, and he came up with an expression for the mean annual rate of non-exceedance of the factor of safety against liquefaction, because we're interested in low factors of safety in this case. We need a probabilistic liquefaction model, such as one by Boulanger and Idris. We're going to sum over all possible peak accelerations and consider all possible magnitudes that are supporting those peak acceleration. If we do that, we get a factor of safety hazard curve. It has the opposite slope of most hazard curves because weak motions that occur frequently give us high factors of safety, and strong motions that occur rarely give us low factors of safety. But if we're interested in a factor of safety of 1, the triggering of liquefaction, we can pick off the mean annual rate of non-exceedance, or its reciprocal, the return period of liquefaction, considering all peak acceleration levels, all levels of ground motion, and all of the magnitudes that underlie them. So is this significant? Well, we can look at a soil profile, an idealized profile, with blow counts ranging from 10 to 30. We put it in 10 different locations with a wide range of seismicity. A lot of span between the left and the right sides of these plots. Some are steeper, some are flatter. The two extremes are Butte, Montana, which doesn't have very many earthquakes at all, and Eureka, California, which has a lot of earthquakes. If we use our conventional procedures, using, say, 475-year peak accelerations and mean magnitudes, we can calculate factors of safety for this site at all of those locations. At Butte, they're very high, above 2.2, 2.3 or so at all depths. And at Eureka, they're very low. Typically here we see that the locations that have higher peak accelerations give us lower factors of safety. But we can also do a probabilistic liquefaction hazard analysis and come up with factor of safety hazard curves, in this case for an element of 6 meters depth. If we do that, we still see that Butte is over on the right with higher factors of safety, and Eureka's on the left with lower factors of safety. If we look at a 475-year return period, we can see that the factor of safety would drop below about 2.2 every 475 years in Butte, but every 475 years in Eureka, it would drop below about 0.3 or so. If we look at a factor of safety of 1, we can calculate the mean annual rate of non-exceedance, or the return period of liquefaction. It would be about 5,000 years at Butte, and would expect liquefaction about every 60 years or so in Eureka. Now, a useful and instructive thing we can do is to take those profiles and adjust the penetration resistances so that we got a factor of safety of 1.2, some constant number, at every depth in every one of those profiles. And if we do that using our conventional procedures, we would conventionally assume that they all have exactly the same liquefaction potential. Then we can do a PLHA and see what the return periods of liquefaction are from our conventional procedure and see how consistent things are. And when we do that, we find that they're not very consistent. There's a wide range of return periods, 300 to nearly 600 years for sites that we would, by our conventional procedures, consider to have the same liquefaction potential. So it shows us that applying our conventional procedures consistently gives us inconsistent actual liquefaction hazards. If we compare Memphis and Portland, those curves happen to intersect at the 475-year ground motion level. And we use a deterministic conventional analysis, and they have just about the same factor of safety. The mean magnitudes are a little bit different, so the factors of safety are a little bit different. But if we consider all the levels of shaking, we find that Portland has a return period of about 400 years, and Memphis is about 600 years. And so with our conventional procedures, liquefaction would actually occur in Portland about 50% more often than it would in Memphis. So there's two ways we can interpret this. One is that the people in Portland are less safe with respect to liquefaction potential than the people in Memphis, or the people in Memphis are being forced to spend more money and design for a higher level of safety than the people in Portland are. It's non-uniform, and neither of those are good situations. If we go out to 2,475 years, there are three that are about the same PGAs, and their return periods of liquefaction vary substantially. If we can interpret this in terms of a relative factor of safety and show that effectively what we're doing is requiring the people in Memphis to design for an extra factor of safety of 1.45 relative to the people in San Jose. So again, we're getting inconsistent results when we're only looking at one level of ground motion. In Washington State, where I live, we can do the same sort of interpretation of a relative factor of safety, and here we did it relative to Seattle. And out on the Pacific coast, on the Olympic Peninsula, we have levels of shaking that are equivalent to 40 to 50% higher factors of safety than we would be requiring in Seattle. Now, that's important. In our state, it's important to our Department of Transportation, because if you look west from Seattle on a typical sunny, clear day, you see the Olympic Mountains on the Olympic Peninsula. And those Olympic Mountains drain to the west, and there are many rivers going down along the coast. There are 13 large ones that are indicated by the red circles there, but there are a lot of small ones as well. And our DOT has to design new bridges and retrofit existing bridges, and they're having to do that with an extra factor of safety of 1.5 or so. And it costs a lot of money that could be spent to retrofit other bridges, maybe in more heavily populated and heavily trafficked areas, than the ones that they're having to spend their money on now. Along the I-5 corridor, our conventional procedures using ground motions with a 475-year return period give us an actual return period of liquefaction of about 400 years. And so if we wanted uniformity within the state of Washington, and we wanted it to be equivalent everywhere to where it is in Seattle, we should be designing for a 400-year return period. Now, whether that's the right number or not, I don't know, but we can determine what the right number should be. And we can do this in other places. Our current approach is to design for specific deterministic factor of safety based on a ground motion with a certain return period. A better, improved approach would be to design for the return period, considering all levels of ground motion that could occur. These PLHA calculations are not terribly complicated, but you have to do a lot of them, hundreds of thousands of calculations, probabilistic calculations. So we need tools to do this. We've developed for the state of Washington a computer program with a nice Windows interface. It handles triggering, lateral spreading, and free field settlement. We're in the process of updating and expanding this and doing it in a way that will make it useful in all states. Kevin Franke at BYU has a program, an Excel-based program called PB Liquefy. I just talked to him, and he said he's abandoning this in favor of a C++ program that's currently under development. So we'll look forward to having that option available before too long as well. There's another way that we can do this. We can define a magnitude-corrected peak ground acceleration by dividing our peak ground acceleration by the magnitude scaling factor. That plugs right into our cyclic stress ratio equation. And we could look and see with conventional deterministic analyses how the factor of safety decreases as that magnitude-corrected peak ground acceleration increases. We can also take our PLHA factor of safety hazard curve and turn it 90 degrees and flip it over, and it would plot up like this. We could then choose a return period of liquefaction, considering all magnitudes, all peak acceleration levels, calculate the factor of safety, come over to our conventional procedure and find the value of PGA sub m that corresponds to that. And that value, if plugged into a conventional analysis, the kind of analysis that people are accustomed to doing now, would give us the same factor of safety that you would get if you'd done a full-blown probabilistic liquefaction hazard analysis. So we could consider this to be a liquefaction-targeted ground motion intensity measure. And we could do these calculations on a grid all across the United States and map those values for different return periods. Or we could develop a website where a user could go, like they do for ground motion hazard information now, put in a latitude and longitude, a site characteristic like VS30, a return period of interest, and get a PGA sub m value. That would allow users to do the same type of relatively simple deterministic calculations that they're doing now and get a factor of safety that's consistent with a defined return period that has all the benefits of the full-blown PLHA. So we've taken this idea to the Building Seismic Safety Council that's responsible for the NEHRP seismic provisions that end up in various codes, met with their provisions update committee where we're very responsive to the idea, support pending validation of the approach. That really boils down to determining how sensitive this factor is, this intensity measure would be to factors that affect liquefaction potential. So we've gotten some fun, well, we would expect some of those factors to be the soil density. We certainly would expect that at a given return period, we're going to have a higher factor of safety for a dense soil than for a loose soil in both a PLHA and in a conventional analysis. And if the effect is similar on both, then we should see that we have the same value of the PGA sub m parameter. Do the same thing with depth and compare shallow and deep cases. We've gotten some funding from the National Institute for Standards and Technologies to do this, to demonstrate this validity, and we're in the process of going through and checking this on sites all across the United States. Here's some examples from Charleston, South Carolina. Here we have a plot that shows the value of PGA sub m as a function of blow counts ranging from 5 to 25. And you can see that the curves are flat, indicating that, at least at this location, there's essentially no sensitivity of PGA sub m to blow counts or to density of the soil. The three groups here correspond to 475, 2475, and 4975 year return periods, and we can see that the curves, still flat, start to separate a little bit. The different curves represent different depths, and so if we look at these results plotted as a function of depth, we see that at these longer return periods, there's a slope there, which indicates that a correction factor may be needed if that effect persists. And we're finding that effect does persist. Here in San Francisco, in a very different seismic environment, we're seeing the same type of behavior. At longer return periods, we're going to need some correction factor, but it seems to be well behaved enough that that correction factor should be relatively simple to implement. So we're looking at this same behavior for 100 sites across the United States. We'll evaluate these sensitivities, develop the correction factors that are needed, and create a program that will allow us to map this parameter at user-specified return periods. So then the user can go enter a site latitude and longitude, VS30 value, get a value of PGA sub m that they use in their conventional calculations, and get a result that's consistent with what they would have had doing a full-blown PLHA. So that's triggering. Triggering is useful. We're interested to know whether or not liquefaction is likely to occur, but we're more interested in the deformations because that's what's going to cause damage. And some of those deformations occur by lateral spreading. Kevin Franke has developed a probabilistic lateral spreading hazard analysis procedures illustrated here for kind of an infinite slope at a 3% gradient. Put that in the same 10 cities at a 475-year return period. We get displacements that exceed 2.5 meters, say every 475 years in Eureka, but only 10 centimeters in Butte. Every 2,475 years, we'd expect to see, for that soil profile, displacements exceeding 30 centimeters in Butte, but up to 5 meters or over 5 meters in Eureka. So Kevin's gone through the same kind of process that we did for triggering and has shown that applying these existing conventional lateral spreading procedures consistently gives us even more inconsistent lateral spreading hazards. So the second phase of the work that we're doing is oriented towards developing improved probabilistic lateral spreading hazard analysis procedures. Our procedure will account for the timing of liquefaction, and we'll be using a vector or multiple intensity measure approach where we can recognize that the soil profile changes when liquefaction is triggered. So we'll use intensity measures that are sensitive to high frequencies when we're up to the point of triggering of liquefaction, and low frequencies to better represent the behavior of a softened profile after liquefaction has occurred. So we'll identify these intensity measures and map them so that they can be used for lateral spreading predictions in a similar manner. If we look at a loss level interpretation and implementation and go all the way to the final result of losses and apply it to a real type of system that may consist of a bridge with abutments and piers and foundations and approach embankments and soil supporting those things, we can see how we can do the full implementation. And so we did this for a profile that had a variable thickness of liquefiable sand, about 10 meters on the right side, only 4 meters on the left side, but a layer of clay under the left side that doesn't exist on the right side. We had a bridge that was designed to Caltrans specifications by an experienced structural engineer who had designed a lot of bridges for Caltrans. It's a box girder structure, 5 spans, supported on 4-foot diameter columns. They were supported on the interior columns by 2x3 groups of 24-inch diameter steel pipe piles, 1x6 groups at the abutments. There were expansion joints and elastomeric bearings at the abutments. There's a break-off back wall at the abutment. The structural model was developed by Kevin Mackey and Boža Stojanović at Berkeley. It's a very detailed structural model using the OpenSea's computer program. We built the foundation model, Pedro Arduino and Hyung-Suk Shin. It is a very detailed foundation and soil model. The piles are represented by PY, TZ, and QZ springs. The soil models, the liquefiable soils, use Ahmed El-Gamal's pressure-dependent multi-yield model and the pressure-independent multi-yield model for the clay soils. When we analyzed the site without the bridge in place, we saw, as we expected, higher displacements on the right side where the liquefiable soils were thicker, and lower displacements on the left side. They both moved towards the center of the model. We also saw that there were some deformations in the clay layer that existed on the left side. Looking at the 475-year ground motions, we ran 10 motions scaled to the same fundamental mode spectral acceleration through this, and we saw, again, higher displacements on the right side than on the left side, which implies that we would have higher bending demands on Pier 4 over on the right side than we would on Pier 1 on the left side. However, the bridge deck was shoved to the left by the deformations that had occurred. And if we look at Pier 1 and Pier 4 did move more at its base towards the center than Pier 1 did, but the bridge moved over 21 centimeters, and so the actual drift levels were higher on the left because of the system response of this bridge. And it really illustrated to us something that we hadn't anticipated in advance. You really get a benefit from analyzing the entire system, because that system behavior can have a great effect on patterns and amounts of damage that occur. Well, it was a complicated bridge structure, and so we had to use a number of parameters to describe its response. So we had 25 engineering demand parameters associated with the bridge deck performance, the columns, pile cap of expansion joints, the back wall of the abutment, looked at vertical offset at the abutments and bearing pad displacements and displacements of the 2 approach embankments. So we analyzed the system with 10 motions at each of 4 hazard levels, and we could choose each of our EDPs, in this case the right abutment horizontal displacement, and see how it varied with the ground motion level. We characterized the median response and characterized the uncertainty so we could develop EDP given IM relationships or response model relationships for all 25 of those EDPs. That allowed us to come up with EDP response hazard curves, which we could combine with the damage models to come up with a damage curve. And so we could have cracking or spalling or buckling of a concrete column, for example, at different levels of deformation, and we'd have different probabilities of each of those damage states occurring for those each level of deformation. We used a discrete damage probability matrix approach, which allowed us to define probabilities of being in different damage states for a given level of response. So for 10 to 30 centimeters of displacement, 60% chance of moderate damage, and smaller probabilities of being in other damaged states on either side. That allowed us to come up with a damage curve. So minor damage we would expect to see for this bridge. And the bridge was located in Oakland, California, where we have a pretty high level of seismicity. That's where the ground motions came from. Moderate damage every 37 years, severe damage every 105 years, and catastrophic damage would be very rare for this particular bridge. Then we could go on and look at losses and use our loss fragility model to calculate a loss curve. And so we did this in conjunction with Caltrans engineers who were experienced at estimating repair costs from bridges damaged by earthquakes, and used again a discrete loss probability matrix where for severe damage, 50% chance of a repair cost ratio, which we defined as the repair cost divided by the replacement cost of the bridge. So for severe damage, 50% chance that the repair cost ratio is 0.5, that your repair costs are going to be half the replacement value of the bridge, and other lower probabilities for other repair cost ratios. That allowed us to produce a loss curve for this bridge. It doesn't include losses due to downtime. It's only repair costs. Downtime losses could be many times greater than the repair costs if it's a bridge that isn't redundant, if it slows traffic down and people have to go a long way around it. Doesn't include losses due to casualties, so it's only part of the picture. For a return period of 100 years, our loss ratio was about 16%. At a 1,000-year return period, 47%. We then looked at this case a little bit differently. This represented a loss curve if liquefaction occurred. We repeated the analyses, not allowing liquefaction to occur. And when we did that, we found that our loss curve looked like this. So at 100 years, the loss dropped down to 5% of the replacement value, and at 1,000 years, it was only 20%. So if that's a $100 million bridge, our 1,000-year loss is $27 million less than it would have been. We can put things in these kinds of numbers and make a determination of whether it's worth investing in soil improvement in order to get that loss down. And these are the kinds of things we can do with this type of framework that we typically don't or haven't been able to do in the past. We also, just to see what would happen, assumed that the bridge was sitting on rock. And when we did that, our damage levels went up a little bit from the case where we're on the non-liquefiable soil property, because the rock foundations were so rigid that they couldn't rock or rotate at the base of the piers, and there was more damage to the piers than there would be with the compliance of a foundation that was on soil. Another big benefit of this type of approach is we can see where our losses come from by deaggregating these results so that we can see what factors are contributing the most to the losses that we would anticipate, and do this at different return periods. So I want to close with some thoughts on what performance-based design and performance-based procedures mean for geotechnical practice. What's it going to require of geotechnical engineers? Well, we have to have a good understanding of kind of the big picture and our role in it. Geotechnical engineering has high uncertainties. We know this, we deal with it all the time, but we're not the only one that have high uncertainties. There's high uncertainties in damage, there's high uncertainties in losses. And so we need to know where we fit in that picture, which means we need to be able to think probabilistically. We can improve our procedures above where they are now by looking at more efficient parameters that are better descriptors of potential damage or response or of loss. So we can come up with problem-specific intensity measures. Different characteristics of ground motions affect different problems differently. We can come up with EDPs, or measures of response, that are more closely related to damage, and damage measures that are most closely related to losses. We can develop improved response models that help us account for uncertainties in better ways. They need to be able to predict deformations. They need to be able to handle both weak motions and very strong motions, because in this procedure, we consider all levels of shaking, not just one. We need improved damage models, and this is a place where we could work profitably with structural engineers to get a better idea of what kind of deformations really cause damage, rather than having somebody tell us they're building this incredibly large structure and it can't move more than 1/10 of an inch. We're going to need some tools to make these things happen. Some tools are available and more will be developed in the future. We need to think about how we're going to use engineering judgment It's a difficult thing for dynamics problems, and I run into this in talking to engineers all the time. It's pretty easy to be conservative when we do, say, a static analysis. You assume a lower strength and you're going to get a more conservative result. I have people call me and say, well, I was conservative, I used a lower stiffness. And it doesn't work that way. That just shifts the frequencies, and it may be more conservative, but it may be very much less conservative or unconservative. So we should aim in these analyses to be accurate, and we can handle conservatism when we deal with uncertainties. There are opportunities with this type of approach for us as a profession. It'll lead to improved products, more accurate response and damage predictions. It'll lead to more consistent and uniform designs and evaluations. We don't need to have this kind of variation across the country from one location to another. It'll let us balance risk. Often our foundation is designed so that it has a different level of risk than the superstructure does. We can balance these things with these types of approaches. We can account for the high uncertainties that we often have to deal with. We can use these techniques to demonstrate the value of our services, to demonstrate that how we can, as geotechnical engineers, do better subsurface investigations, do more detailed analyses, reduce uncertainty, improve accuracy, and show how that benefits in the terms of that an owner can understand and result in lower losses. So the benefits of investing in improved investigations, laboratory and field testing, and more detailed analyses can be demonstrated in those types of terms. Be more involved with the codes development. The performance-based approach gives us an incentive to go beyond minimum code requirements so that we can provide this kind of values to our owners. If we implement these procedures into codes or elements of them into codes, it can allow us to reduce uncertainty and our ability to reduce uncertainty through the types of detailed analyses that we can and would like to do to benefit our client. Thank you very much for your attendance.